Hey guys, so today we're going to implement this binary tree that we talked about in the theory videos. This is going to be in two parts because it's still not bad though. So in this one we're going to solely focus on insertion, and then in the second video we're going to do search and delete. There's going to be deep dives at the end of both though. I don't want to leave you guys hanging with lessons, so I'm going to go ahead and post the lesson for this one, and then I'll append the lesson. I'll append the second lesson to the same GitHub, right? So you have everything in one spot. Also, guys, this is the third time I've recorded this video because I start writing code and I get really into it. And sometimes you guys may see me looking over here. The reason I'm looking over here is because my recorder is set up, my screen is set up over here showing what I'm recording. And I get typing, and then the next thing I know, I look over and like half of my code you can't see because it's gone beneath the screen because it doesn't scroll. And so maybe I can do something my recording setup. I'm new to this shit, guys. So if you guys have any like automated solutions to that, I use OBS. This is a Linux tool. Maybe I can do something with that. But yeah, like any way to automate like screen scrolling so I don't have to keep looking over here to make sure that you guys can see the code, that would be awesome because it sucks. But yeah, so enough bitching. Let's write this. Let's do this. Okay, so the first things first is we define the tree node, right? Because these are the things that make up our binary tree, and they're going to contain a value. They're going to have a left child, and then a right child. Okay, and we're going to talk about option and box in the notes. All right. Now we got to implement it. Always got to implement it. So create the old constructor. Return itself. Tree node value. Oh, and then also this is going to be, so it needs to take a value. Left is going to be none, of course, and right none, of course, because it needs to be empty. All right. Now the binary tree. Yeah. All right, root, same thing. All right. Now, you got impl on it. Got an impl on it. I need to make me a shirt, man. It's an impl on it. And okay. And none. All right, okay, now let's do this. Okay, so let's start adding nodes to the tree. And so this is going to be the method that we use to put things in the tree. Okay, so it's going to be add. Okay, it's going to take a mutable reference to self and a value. Now we got to define a new value. Okay, and it's going to be tree node new value. Okay. And I'm going to walk through some of this recursion step because this is a very clear, this code is very easy to reason about the recursion, making it very easy to debug. And so I'm going to walk you through it because if you're having a hard time grasping recursion, I think this may help because the recursion is very clear in this code. Okay, so we're going to match on root. Now, okay, so imagine we got our tree, it's empty, there's nothing there. Okay, so and match. We tell match what we're expecting to get back. Okay, so we're using an option so we could get none back. All right, so if we get none back, well, that means there's nothing in the root. That's not good. So we immediately place something there because the first node inserted is the root node. So we immediately place it. All right. Now, what else could we get back? Well, we could get back a mutable reference to a root node. And that means that the root node, well, that means that it's there, right? That's what we're expecting back if the root node is there. Now, we're going to do insert node, okay? Now, what this is going to be, we're going to create we're going to create a parameter named current. And this is going to take a mutable reference to a tree node, to a pointer containing a tree node, and then our value is going to be a tree node. Okay, so all right, now, okay, so we're going to build out the insert node method, and then we're going to walk through the recursion. Okay, so what are we doing? So if we'll name this new node. All right, that makes more sense. Okay, so if new node's value is less than the current node's value, well, even without maybe not necessarily knowing what we're doing here, what do we know, right? If the new node is less than the current node, what does it do? It goes to the left. Well, then you just match on current.left, right? Okay, what if it doesn't? What if it's greater? Well, it goes down the right. I mean, dude, it's a script, man. Like, Rust being so expressionate, man, it makes this stuff so easy to do. And so, what could we get back? Same thing, none, man. We could get none back, and if nothing is there, well, we're going to insert it because it's down the left tree, so we know it's less than the root, so it needs to go down here. So we're just going to insert it. Okay, what else could we get back? Well, we can get back a mutable reference to a left child. All right, left child could be there. Now, what's going to happen when this happens? Well, the same thing. Same thing. What happens on the right? Well, what could we do? None. Current.right. Well, we know that this value is bigger because it's being pushed down the right, so we need to go ahead and place it if nothing is there. Same thing. And then guess what? Guess what? You could get back some reference to a mutable right node. And guess what? You do the same thing. You do the same thing. You do the same thing. Let's walk through some recursion. So what's happening? Okay, so we're matching on root, so we get nothing back. Okay, so if nothing comes back, well, this value that we pass, it's just going to be the root node. The first node's the root. Okay, so that first root node's been placed there. So if we come back through with a new value, well, we're going to have to compare it to the root, right, to see which way it goes. So we're going to pass root node has the current node, and we're going to pass new value has the new node. So if the new node is less than the root node, well, we're going to go down the left. Well, if there's nothing there, we're going to go ahead and replace it because we know it's less than the root node. We just need to go ahead and place it. Okay. Now, say that we go back through and it's something is there. Well, we pass left child has the current node and new node has the new node. So, if the new node is less than the current left node, we still go down the left side. We're just going down the left side of that node and then doing the same thing. If nothing is there, we're placing it. If something is there, we're doing the same comparison, and it's the same thing on the right. Like, it's stupid easy. It's stupid easy to reason about. Like, the code, the code has it's got a beauty to it. So yeah, it's very easy, guys. Super easy. Okay, so now let's go over to the implementation in main. Yeah, so we're creating a tree and we're inserting the values and then printing it out. Okay, so let's see what it looks like. Okay, so let's not pay attention to the visual representation yet. Let's go ahead and go over here, right? So 10's being inserted first, so it should be the root. Here we have the root node and its value is 10. Good deal. We're inserting 5. 5 is less than 10. So 10 should be to the left of 5. 5 should be to the left of 10. So we see that 10 has a left child and its value is 5. Good deal. So 15, let's only worry about the left side. 15 is going to be pushed off to the right. 3 is less than both 10 and 5, so it's going to go to the left of 5. So 5 should have a left value of 3. Yep. And then we insert 7, less than 10, greater than 5 though. So 5 should have a right value of 7. There it is. And then 10, or 15, sorry. 15 is greater than 10. So here is the left child of 10. Here is the right child of 10. And we see that it has a value of 15 and no left or right children. So we are successful. All right, let's look at some notes. Okay. Okay. Binary trees. All right, so these are our data structures. We've got our tree node. And so our tree node represents a node in the tree. It's got a value, and a left child and a right child. And the nodes restored has tree nodes wrapped in a box, wrapped in an option. Okay, so, you know, part of these videos is to kind of help you learn a little bit of Rust too. So I like to go through some of the Rust stuff. You can't go through it in every video because it would just blow out your time. But yeah, so option, this is a Rust enumeration that returns something or nothing. And then box is a pointer that stores data on the heap. We do this because of some compiler requirements. If you don't know the difference between stack and heap and why you would use one memory over the other, I'm actually going to make a video about it because that is some core fundamentals right there that you really need to know. So that video, if it's up, go check it out. If not, you know, that stuff, you need to know that stuff. Okay. Now, and then our binary tree just holds the root. Okay, so we create the new tree, whatever, you know, just creating a tree with an empty root. And then, you know, partial ordering means you can compare two T's or two generics with, you know, less than or greater than. And okay, so inserting the value. I mean, honestly, guys, what I talked about in the code run through really covers most of this, how all of this works. So yeah, we see if root is none, we immediately make the new node the root. If there is a root, we call insert node with the existing root node and the new node, and then we compare the new node's value to the current node. If it's less, we go down the left, and then if it's greater, we go down the right. Okay. And this mutable box, and this is mutable because what this does, you'll see down here, this allows us to insert children, right? That's why it's mutable. All right, guys, and so yeah, that's it. So in the next video, we're going to do search and delete. If you have any questions about this, let me know. Help each other out in the comments. Ask respectable questions to get respectable answers, and I'll see you in part 2.